Here's the challenge. Keep a distributed cache's key-to-server mapping stable enough that adding one more machine doesn't touch data it has no business touching. Every engineer's first instinct is the same. Hash the key, mod it by the number of servers, done. And that instinct is correct, right up until the server count changes. Add one node to a 4-node cluster, and something strange happens. The vast majority of keys point somewhere new, even though nothing about the data changed. Not eventually, immediately, the moment the count shifts, because n was baked into every single mapping. So the real question isn't how to hash a key. It's, can you design a mapping that doesn't care how many servers exist at all? Modulo hashing is exactly as simple as it sounds. Take a key, hash it to a number, divide by however many nodes exist, and the remainder tells you which node owns it. Hash, key, mod n. It's fast, it's stateless, and for a cluster whose size never changes, it's completely correct. The problem shows up the moment n changes. Picture a 4-node cluster and add a 5th node for more capacity. Routine, healthy. Before the math, how many of the existing keys keep the same owner when the new node joins? Almost none keep their owner. The modulus changed from 4 to 5, and hash, key, mod 4 agrees with hash, key, mod 5 only by coincidence. Work it out. Roughly 3 keys in 4, n-1, over n of the total, get reassigned simultaneously the instant the node joins. Every one is now a cache miss on whatever node thinks it owns it. Don't take that ratio on faith. For real hash values, 17, mod 4 is 1, mod 5 is 2, moved. 88, mod 4 is 0, mod 5 is 3, moved. 233, mod 4 is 1, mod 5 is 3, moved. Only 42 lands on the same server either way. Mod 4 and mod 5 both give 2. 3 of 4, exactly as predicted. This isn't hypothetical. Real incidents like JPL's site crashing under Shoemaker-Levy comet traffic and IBM's during Deep Blue versus Kasparov are exactly what motivated the field's search for a fix. Here's the reframe. What if a key's owner never depended on n at all? Instead of computing an owner from n, hash both keys and nodes onto the same ring, positions wrapping back to 0 at the top. A key's owner is whichever node you reach first walking clockwise from its position. That's a purely local relationship to its nearest neighbor, never a function of how many nodes exist. Why does that fix the disruption? A new node only intercepts keys that used to reach its clockwise successor, the arc between itself and its predecessor. Every key outside that arc still hits the same node, walking clockwise, exactly as before. N was never part of the calculation. Take a concrete ring, 4 nodes at 10, 90, 170, 250 out of 360. 6 keys land at 5, 45, 95, 180, 230, 300. A 5th node joins the ring at position 100. Which of the 6 keys changes owner? Only one. The key at 95, previously owned by the node at 170, the first one reached walking clockwise from 95, now belongs to the new node at 100, closer along that same walk. Every other key, at 45, 180, 230, 300, even the one just past the new node at 5, keeps exactly the owner it had. Not approximately unaffected. Provably unaffected. Walk the ring for any of them, and you hit the same node as before. This is a real, formally proven property, not a rule of thumb. David Karger and his co-authors named it monotonicity in the 1997 paper that introduced the idea. Adding or removing a node moves only the minimum fraction of keys the change actually requires. Now run it in reverse. Node E leaves the ring. Which of the 6 keys changes owner this time? Only one again. The key at 95, currently owned by E, reverts to the node at 170. The first one reached walking clockwise once E is gone. Every other key keeps exactly the owner it already had. There's still a problem this ring, on its own, doesn't solve. Each node's single ring position is placed at random, which means the size of the arc it owns is also random. One node might get a wide arc and a heavy share of the load. Another might get a sliver. The ring fixes which keys move. It says nothing about whether the load stays fair. So, how do we keep the ring's load fair, given it has to stay local? More physical nodes doesn't help. Each still claims one random position, so the variance just spreads across more machines. A fixed key range partition would balance perfectly, but gives up the ring's whole reason for existing. Membership changes become manual reassignment again. The fix: give each node several ring positions instead of one. Virtual nodes. Total load per node becomes many independent random draws instead of one, averaging toward fair the same way any larger sample does. Doesn't that just multiply the ring metadata? Yes. A bounded, linear cost for fixing an imbalanced raw node count structurally can't touch. Virtual nodes cut this both ways. Without them, if a node fails, its arc doesn't disperse. It lands entirely on one neighbor. If E goes down, every key in its arc becomes C's problem alone, risking a cascade if C was already near capacity. With many positions per node, that same failure spreads across many different neighbors instead. Two sharper alternatives. Briefly, rendezvous hashing skips the ring entirely. Score every node per key, at the cost of 1 hash per live node, per lookup. Or rehash in the background. Hides the latency, not the near total remap. Here's both halves in code. Adding a node hashes each virtual node token into a Java tree map keyed by hash value. To route a key, hash it, then call ceiling entry for the first token clockwise, or, if that's null, wrap to the very first entry. Both are backed by a red-black tree, so lookup is logarithmic in virtual node count, never a linear scan. Of virtual nodes, rendezvous hashing and background rehashing, which one actually fixes the balance problem, and why do the other two fall short? Last refinement. How many positions, placed how? Pure randomness needs a lot. Cassandra's 2.x default was 256 per node, and every extra token couples that node to more neighbors, so one failure touches more of the cluster. A deterministic allocator hits the same balance with far fewer. Two decisions, worth restating plainly. First, virtual nodes over a single ring position per node. We gave up ring size, more entries to store, and walk per added position. That's worth it. A bounded, linear cost fixing an imbalanced raw node count can't touch. We'd revisit this if node capacity gets wildly heterogeneous, or the ring walk cost itself starts to dominate. What eventually happened to Discord? Second, a deterministic allocator over pure random placement. We gave up simplicity. It has to run at Bootstrap and on every topology change, instead of each node just picking its own position. That's worth it. Same balance as Cassandra 2.x's 256 random tokens per node, with far fewer, shrinking any single node's failure blast radius. We'd revisit this if topology changes so often that recomputing the allocation becomes a real, recurring cost. This same mechanism runs in production today, solving 3 genuinely different problems. Amazon's Dynamo partitions its key space with consistent hashing to fix exactly the load imbalance and heterogeneous capacity problem virtual nodes solve here. Dynamo's paper is what popularized virtual nodes in production, building on Karger et al.'s original 1997 construction. Apache Cassandra walks the ring clockwise to find enough distinct nodes to satisfy its replication factor. And its own version history is the real allocator story. 2.x's random placement, 3.x's deterministic fix. Discord routes session lookups for millions of concurrent users through a consistent hashing ring and hit a different wall entirely, not rebalancing, but the raw cost of walking the ring itself at enough scale. Amazon's Dynamo, Apache Cassandra, and Discord all build on consistent hashing, the same mechanism solving 3 different production scaling problems. The pattern this instantiates: locality-preserving hashing. Servers own arcs, not slots. A key's owner is whoever you hit first walking clockwise from its position. The same outcome. A membership change only perturbs nearby entries, never a global recompute. Shows up in Chord's finger table routing and in rendezvous hashing, which reaches it differently. No shared coordinate space, just every node scoring each key and the max scorer winning. The test: does the ownership function take the total member count as an input? If yes, every membership change is a global event by construction. How this evolves: as node and lookup counts both grow, ring lookup itself, not rebalancing, can become the bottleneck, exactly what Discord hid in production. What's preserved? The ring's ownership mapping never changes, only where it gets evaluated does. Consistent hashing doesn't make rehashing cheaper. It makes rehashing local by putting keys and nodes on the same ring and only ever remapping the arc next to whatever node just joined or left. Self-test. Name what changes when a node joins the ring and what stays the same for everyone else. For a node with 10 times its peer's capacity, what would you do differently? Give it proportionally more virtual node positions. If you're asked to draw this on a whiteboard, start with a circle, that's the ring. Plot 2 or 3 physical nodes around it. Then sketch a couple of virtual positions per node, so the interviewer sees you know real systems don't use just one. Drop a key onto the ring and draw one arrow clockwise to its owner. That's the whole mechanism in 4 strokes. 3 questions worth sitting with. What's the weakest assumption this design depends on? What breaks first if lookup rate alone climbed far higher, with no new nodes at all? And does a balanced ring even help if a single key goes viral?